The Earth's atmosphere and oceans are inherently chaotic, a nonlinear nature where the finite uncertainty or error in the initial stage will ultimately grow into an unpredictable future, so-called butterfly effect. To measure the time extent where the forecast state is still reliable, i.e., depends on the initial conditions. The concept of predictability was introduced in the 90s by Rowland. The predictability is generally defined as the timing where the forecast ensemble density, a conditional probability of the initial states, is statistically distinguishable from the climatological distribution. Such a definition links conditional probability and ensemble forecast together, which enables the discussion of predictability. For example, they discuss the predictability and actual prediction scale of MJO. Also, we can talk about the predictability of monsoon. Finally, we can investigate the connection between forecast probability and ensemble spread. And recently, someone talked about the predictability of tropical cyclones track density in S2S with forecast. Similar concepts can be generalized into various different fields, such as the discussion about the evolution and prediction of ecosystem, and the predictability of human mobility across a large segment of the population. To furthermore quantify predictability, that is, distinction between rho t and rho infinity, it emerges the need to define a distance between the two distributions, i.e., how different two distributions are. Traditionally, we may use root mean square error, or called RMSE, to examine the distance, and it tapers toward zero as the evolution of rho t reaches the equilibrium. This metric confines the second moment of rho t and rho infinity, leads to an L2 convergence for distributions. However, the link between RMSE and continuous flow, whose probability distribution obeys the Liouville equation, is implicit. Thus, proposed a metric based on the concept of entropy in information theory, the difference in Shannon entropy between current rho t and climatological rho infinity, given by the difference of two Shannon entropies. As a quantified measure, the larger the uncertainty, that is to say, the spread of ensemble, the larger the Shannon entropy is, while entropy of the rho infinity stays the same for the sake of stationary climatology. Furthermore, this evolution of Shannon entropy has deep connection with the Liouville equation by sharing the same term, the divergence of the continuous flow, i.e. the trajectory of ensemble over the phase space. In our study, we will investigate the interconnections among Shannon entropy, phase space divergence, and predictability limits through their links with the Liouville equation. Furthermore, we will answer whether divergence and Shannon entropy give us the same definition of predictability. We conduct several idealized experiments with L6T3 and L96 models in case of full and reduced dimension to demonstrate the connection between metrics above. With this experience, we are able to provide new insight on the physical interpretation among three concepts that we mentioned in the beginning of this paragraph.